Welcome to the Deep Dive. We're the place where we sift through articles, research, piles of notes, really, to pull out the insights you need to know. And today, well, we're tackling maybe one of the biggest questions out there, truly mind-bending stuff. What was actually here before the Big Bang? You know, the basics, right? The Big Bang Theory. Our best explanation for how it all began about 13.8 billion years ago. Starts with this idea of an initial singularity, then boom, space, time, matter, energy, everything erupts. And classically, physics kind of tells us that was the start of time itself. So asking before, it's almost meaningless, like what's north of the North Pole. But, and this is the cool part, modern science, with amazing new observations and some really out there theoretical physics, starting to poke holes in that. So our mission today, explore how the Big Bang might just be, chapter one in a much, much bigger cosmic story.
It really is a fundamental challenge. I mean, the standard model, general relativity, it describes everything emerging from that singularity. And like you said, within that classical picture, time begins there. It creates this conceptual wall. We just can't use that physics to probe before. The question doesn't even compute in that framework.
That wall, yeah. But okay, right after that initial moment, things happened incredibly fast, didn't they, this inflation phase?
Extremely fast. An exponential expansion, faster than light speed, just for a fraction of a second. Then things settled into this super hot, super dense soup. That's when the first light elements, hydrogen, helium, started to form.
And then things cooled down over, hundreds of thousands of years?
Right, until about 380,000 years after the Big Bang. That's a key moment.
Yeah.
The universe cooled enough for neutral atoms to form protons grabbing electrons. And crucially, this meant photons, light particles, could suddenly travel freely without just scattering off electrons constantly.
So the universe became transparent.
Exactly. And that light released then is what we now detect as the cosmic microwave background, the CMB.
Which isn't just old light, it's more like a photograph, right?
Precisely. It's a snapshot of the infant cosmos. Think of it like a cosmic blueprint. It has these tiny temperature fluctuations representing density variations, which are basically the seeds of all future structures, galaxies, clusters, everything.
Yeah, we're getting incredibly detailed pictures of that blueprint now.
Mm-hmm.
Instruments like the Atacama Cosmology Telescope, ACT.
Yeah, ACT and others are giving us these high-resolution maps. We can see not just where matter was, but how it was moving. It's helping us connect the dots, from those very simple early conditions to the complex cosmic web we see today.
Connecting the dots, but also finding things that maybe don't quite connect. You said hints earlier.
Well, yes. The more precisely we look, the more we find things that challenge the standard pictures and potential cracks in the foundation.
Okay, let's get into those cracks, because it sounds like more than just hints. You've got telescopes like JWST, right?
The James Webb Space Telescope, yes. It's already finding galaxies that seem surprisingly massive and, mature, much earlier in cosmic history than our models easily allow for.
So galaxies formed faster or earlier than we thought?
It appears that way, yes.
Mm-hmm.
Which forces us to rethink how galaxy formation works in the early universe. But maybe even more puzzling are these gigantic structures being found.
Like the Big Ring, I read about that. And the giant arc.
Exactly. These are enormous arrangements of galaxies or galaxy clusters stretching billions of light years across. They are just vastly larger than anything predicted by our standard cosmological models, which assume the universe should be fairly uniform, homogeneous on the largest scales. That's the cosmological principle.
Okay, so if the rulebook says things should be smooth and evenly spread out on that scale, but we're seeing these massive, cosmic continents, what does that mean? Does it break the rulebook?
It certainly bends it, maybe even breaks it. I mean, these aren't small discrepancies. They suggest something fundamental might be missing from our models. Is the cosmological principle itself wrong? Or is there some new physics needed to explain how such structures could form?
Wow, and what kind of new physics are we talking about?
Well, people speculate. Maybe things like cosmic strings, these hypothetical, incredibly dense threads left over from the very early universe could have seeded such large structures. Or some even suggest they could be echoes or influences from a previous cosmic cycle if such a thing exists. It really opens up some exotic possibilities.
Got it, possibilities. And it's not just structure, is it? There's also the whole mystery of dark energy. Remind us quickly.
Right. So about 68% of the universe's energy density is this dark energy. It's the stuff causing the expansion of the universe to accelerate.
Pushing everything apart faster and faster.
Correct. And for a long time, the simplest model was that this dark energy was constant, a cosmological constant, as Einstein first proposed, though for different reasons.
What now?
Well, recent data, particularly from the Dark Energy Spectroscopic Instrument, DESI, is giving hints. And I should stress they are still just hints that dark energy might not be constant. It might actually be evolving, perhaps weakening over cosmic time.
Wait, weakening? The force pushing the universe apart is losing steam.
Possibly. It's still early days for this data, needs more confirmation.
But if it is weakening, I mean, that changes everything about the future, doesn't it? Our whole picture of the universe endlessly accelerating apart might be wrong.
It throws it into question, absolutely. If dark energy fades, the acceleration could slow, stop, or even reverse eventually. It could lead to a big crunch where the universe collapses back in on itself, or maybe a big rip scenario becomes less likely, or something else entirely. The key takeaway is if dark energy isn't constant, that points towards new physics beyond our standard cosmological model. It's dynamic, not static.
Okay, so we have galaxies forming too early, structures that are way too big, and maybe even dark energy changing its strength. Plus, we still have that fundamental problem, the Big Bang singularity, that conceptual wall you mentioned.
Exactly. All these things together, the observational puzzles and the theoretical incompleteness at time zero, they naturally push scientists to explore alternatives. Ideas that might incorporate quantum gravity, maybe suggest time didn't actually begin at the Big Bang.
So what are some of these alternative stories?
Well, one interesting, though less mainstream idea comes from Richard Lewy. He proposes a kind of sequence of mini-bangs, or transient singularities, instead of one single Big Bang.
Mini bangs, like ongoing bursts.
Sort of episodic bursts of matter and energy entering the universe. What's neat is that he suggests this mechanism could potentially explain phenomena like dark matter and dark energy without needing, mysterious invisible stuff.
So it's trying to solve multiple problems at once. But is that testable? Can we look for evidence of mini bangs?
He argues yes. It might predict subtle discontinuities, like little jumps, in the relationship between how far away galaxies are and how fast they're moving away from us, the redshift distance relation. If we saw those specific kinds of jumps, it could be a fingerprint of these events. It's a very different picture of cosmic evolution.
Okay, that's one angle. And then there's Roger Penrose, the Nobel laureate. His idea sounds even more radical. Conformal cyclic cosmology.
Yes, Penrose's CCC. It's definitely controversial, but also deeply thought-provoking. The core idea is that our Big Bang wasn't the beginning, but just one beginning in an infinite series of universes, or eons.
So universes cycle. One ends, another begins.
In a way, yes. He suggests that the infinitely expanded, cold, empty state of a universe's far future becomes, through a mathematical transformation called conformal rescaling, the hot, dense Big Bang singularity of the next eon. It tries to elegantly connect the ultimate future with the ultimate past.
And he thinks there might be evidence, like traces of the previous universe in ours.
That's the most controversial claim. Penrose suggests there could be specific patterns, like concentric circles of low variance visible in the cosmic microwave background. He calls them Hawking points, potentially, related to black hole evaporation in the previous eon.
Wow. But practically, how much real traction does that have? Finding those specific signals in the CMB data sounds incredibly difficult, right? Distinguishing them from just random noise.
You've hit the nail on the head. It's extremely challenging. While the theory is mathematically sophisticated, the observational evidence is highly debated within the community. Many cosmologists are skeptical that the claimed signals are statistically significant or uniquely predicted by CCC.
So it highlights a fundamental limit, doesn't it? Even with our best telescopes, we can't directly see beyond the CMB, beyond that 380,000-year mark, let alone before the bang itself.
Correct. We rely entirely on indirect clues. Patterns in the CMB, yes, but also how galaxies are distributed on large scales, how cosmic expansion changes over time. We're essentially looking for faint whispers or echoes of whatever might have preceded our known universe.
It really feels like this whole quest is right at the edge, where science meets maybe philosophy. It's this interplay between hard data, bold theories, and just deep speculation about existence.
Absolutely. And it underscores why progress likely requires breakthroughs in fundamental physics. We probably need a working theory of quantum gravity, something that unifies general relativity and quantum mechanics to truly understand the singularity and what, if anything, came before.
So to wrap up, the Big Bang model, it's still our cornerstone, incredibly successful.
Definitely.
But it's looking less like the absolute first page and more like perhaps the start of the current chapter, a gateway to deeper, older mysteries.
That's a good way to put it. It frames the beginning of our observable universe, but the story might be much longer.
Which leaves us with a pretty profound thought to chew on. If our universe is just one part of some grander, maybe infinite cosmic narrative, what kind of echoes or remnants from previous chapters might we eventually learn to detect? Or perhaps, are we already interacting with them in ways we don't even recognize? Something to think about. We'll leave you with that until our next deep dive.